Hi everyone, I'm Dilo, a physics PhD student from the University of Illinois Urbana-Champaign. It's a great pleasure to have the opportunity to share our recent work on quantum dynamics by solving probabilistic differential equations via autoregressive neural network with George Chen, Juan Kraskula, and Brian Clark. I will first present the key ideas and formulation of our approach, and the other first co-author, Joel, will discuss the algorithms and the numerical experiments. One of the recent exciting progress in science and technology comes from quantum physics. The dynamical process of quantum mechanics appears in various contexts of quantum science and technology. For example, we have quantum dynamics of molecules and atoms, which correspond to important physical and chemical reactions. We have quantum dynamics and time-dependent control in the implementation of quantum computer and quantum devices. In general, quantum dynamics can be described within an open system framework, where we have a system of interest, as well as a dissipated environment coupled to the system. Even though there's great interest in exploring quantum dynamic phenomena, there are also great challenges imposing from the nature of quantum physics. The dimensionality of the space that describes the quantum dynamics grows exponentially with respect to the number of particles, which results in difficulties in direct classical simulations. Interestingly, the advancement of machine learning in recent years provide powerful methods for tackling the curse of dimensionality. One idea we would like to explore is to utilize the power of modern neural networks, such as transformer, to simulate quantum dynamics in a compact representation. In standard quantum mechanics, quantum dynamics is described by high-dimensional quantum master equations on the dense matrix rho. A dense matrix rho is a positive semi-definite matrix with trace 1, and the operator L is called the Liouvillean superoperator, which depends on the physical system. In this paper, we have proposed an exact formulation with the quantum information concept PLBM, which maps the quantum master equations into high-dimensional probability differential equations. Under this formulation, the dense matrix will be mapped to a high-dimensional probability distribution with the same exponentially growing dimensionality, and the superoperator will be mapped to a high-dimensional matrix.
The power of our probability formulation comes from the fact that we can efficiently parameterize probability distribution with modern neural networks. In this work, we parameterize the high-dimensional distribution on multiple qubit measurements with autoregressive transformer. The autoregressive transformer constructs the probability distribution as conditional probability distributions over different measurement outcomes AI. Each AI has 4 choices from 0, 1, 2, and 3. And due to the autoregressive nature, AI can have exact sampling through P of AI depends on A1, A2, all the way up to AI minus 1, which is much more efficient than Monte Carlo sampling and other conventional approaches. To simulate quantum dynamics within the probabilistic formulation, we have proposed a variational algorithm based on the forward-backward method. The key idea of the algorithm can be described in the following graph. We initialize the probability distribution at t equals 0 as transformer p0 theta. At each time step tau, we have an existing transformer representing distribution pt. Our goal is to update the transformer representation at t plus 2 tau. This is done by forward and backward matching the evolution as the graph shows. This will give rise to the cost function so that we can variationally optimize the transformer parameters. We have benchmarked our approach in different scenarios. In general, we have the Lindblad operators with 2 terms written as follows, where gamma is the dissipative term. We first tested in the case of different dissipations. It is shown that our methods simulate the quantum dynamics accurately in different dissipative regimes from open to closed systems compared to the exact solution. Next, we compare the performance of different transformer architectures in terms of the hidden dimension and hidden layer. It is found that different architecture achieves consistent results, which imply the different autoregressive network has sufficient representation ability. In summary, we have developed a general formulation to study quantum dynamics through solving high-dimensional probability differential equations. Our approach provides an efficient way of simulating both open system and closed systems without regressive transformer. Meanwhile, our method could be further applied to solving high-dimensional probability differential equations in various classical contexts. We believe our approach will be important for exploring quantum dynamics in the future. Thank you.